Welcome to the third episode. I'm your host, Shabik Deb. AI is making intelligence digital. Crypto is making institutions digital, and digital intelligence requires digital institutions. The mission of this show is simple. Talk to the most fascinating entrepreneurs and intellectuals shaping this future and extract lessons that you can actually apply. Today's episode is about one of the most ambitious protocol upgrades in crypto right now, Alpenglow, the redesign of Solana's consensus and data propagation architecture itself. To explore that, I'm joined by Roger Wattenhofer, Kobi and Quentin Kniep from Anza, the team leading the design and implementation of Alpenglow. Roger is also a professor at ETS Zurich, and Kobi and Quentin previously did their PhDs in Roger's group. Roger, Kobi, Quentin, welcome to the show.
Hey, great to be here. Thanks for having us.
Today we'll cover three things. First, what was broken or limited about the TowerBFT and so proof of history. Second, we'll go over how Alpenglow actually works. And the third, what this changes in practice for validators, for MEV, for developers when finality collapses to hundreds of milliseconds in the Solana ecosystem. So I want to start with the story. So you guys studied Solana's consensus from the outside. You wrote a paper about that how Solana could be halted, the previous consensus architecture. So how do you go from writing a paper on how to halt Solana's consensus to actually building what may be the largest redesign of Solana's core protocol since the launch?
I can take this. I mean, we had this student project, basically. This was at the university. Still, we not only looked at Solana, we also looked at other blockchains. And we just tried to find maybe things that could be improved or holes. And we found something we thought was a bit wrong about Solana back then. And then, the founder, Solana founder himself, contacted, I think, Kobi, right? For some reason. So yeah, maybe Kobi. And he contacted Kobi, and then we kind of got to talk with each other. They sort of knew this problem already that we were describing in the paper. This was not news to them. So they had already some, let's say, bug fixes about this problem. But still, the founder was very open to talk with us, and we discussed the protocol a bit more. And eventually we got some homework from them to show that we are worthy. And eventually they hired us. That's sort of the story, I guess. But Kobi might know more.
I think it was a pretty interesting meeting of very different worlds, because we come from, like, mostly, right, we did PhDs and we write papers and we talk to academics and they think about theoretical problems, right? And Solana was known, and it's still known and very much into like engineering and problems that are painfully real. All right, so the point I want to make is that they thought about like some properties they want to exhibit in practice. I want to mention, for example, like really pipelined distribution and execution of blocks. Okay, that's, I think, something that Solana pioneered. That's really nice. And I haven't seen this kind of thing in academia. Anyhow, my point is, they have their practical properties, right? And but the sort of theoretical rigor behind it was neglected, right? And then we came in and we said, oh, look, there's this thing in there that's not so nice theoretically, right? And then I think it was very nice that we got to talk to people who, like, as I said, they know, and now we do know, and we think about problems that are real in practice and very important in practice, but then we can also contribute so that it's now theoretically sound.
I see. And is that the origin story of the whole Anza Labs also? Like you like when you guys moved over, that's like you bootstrap the Anza Labs itself.
I mean, Anza existed already before. So this is not just us. This is about 50, I would say, people. This is kind of the people who are behind the Agave protocol, which is the main protocol for Solana.
Yeah, the
And
split basically happened before and was kind of independent of
Yeah.
us joining, right? We just joined Anza at that point because Anza was already going to be the place where Agave will be developed.
but they did call us the research lab of Anza then, right? So that's sort of like, that was new somehow. It's not even that we are the only ones with PhDs, but there's not too many, I would say, in
Yeah,
Anza.
lower PhD density than in maybe other labs.
Okay, so maybe it's worthwhile to talk about, given this origin story, that what was broken in their like previous protocol in the proof of history and the TowerBFT. What exactly did you guys found? And it seems like they already knew about it, but what was exactly the problem?
Well, I mean, so the current protocol basically produces blocks. It has slots. It produces blocks. Some leader has the opportunity to produce a block for a slot. And the thing they neglected early on, in some sense, is that the leader could just equivocate to have two blocks for the same slot, essentially, in some weird way. This has also to do, I would say, with how protocols are often specified, right? So when you go to actual companies, then sometimes the code is the specification somehow. But we kind of looked at specifications we could find, and there it was described still in the old way. Yeah. But that's, I would say, the root of the problem now.
I think one reason they might have neglected this somehow is probably also Turbine, right? Because Turbine at least makes it harder, or seems to make it harder to equivocate for the leader. And you might be, you might think that that it's enough and you can rely on that, but you still need to handle equivocations even with Turbine.
Isn't Turbine like modular enough? Like it's like a data dissemination protocol, right? Which is different from the major consensus part that is going on, the TowerBFT and the PoH. Is it not easy to analyze them separately?
True. I think what Quentin says is that they didn't worry about it so much because Turbine would solve the problem almost by itself. Right?
Yeah.
You know, like you could argue if you have a good data dissemination protocol which has fault tolerance built in, right? Then you send around stuff, and if you really equivocate on the same slot, then people would notice that somehow, right? It's very hard to do that actually.
Given that this is the motivation, we should switch gears to talk about how Alpenglow works.
These were two things that Solana cares much about, right? They want to have many transactions per second and fast confirmation. And they want to have a good security model. So we added something new here, which we call this 20 plus 20 security model, which is 20% Byzantine stake and 20% crash failures on top of that, which is somewhat different from the typical 33% that most others have. So in some sense, a bit worse for Byzantine failures, but a bit better for crash failures.
So to just summarize on this, the three things that you said, these are the three parameters. Throughput, they want to increase the throughput, decrease the latency, that's the second parameter. And the third one is about this security resilience, in which you have added now a crash fault nature to that. It's not just Byzantine, but it has Byzantine plus crash fault. So these are the three.
And I would say the first two were, this is like the motto of Solana, right? They care a lot about this increased bandwidth, reduced latency. That's what Solana is about, I would say. And the third we added, right? But I think it's kind of like we didn't add this because we wanted this so much. We thought about it and liked the idea to have crash failures on top of it, because crash failures seem to be a lot more common in the real world than actually Byzantine failures, at least when we look at how blockchains are used these days. But
crash fault is something that is not generally cared in the academic land. Am I getting that one correctly? And in the real world, it is much more prevalent.
I think it is. I mean, I'm talking as an academic here, but we see crash faults all the time. But like, when was the last time you actually saw Byzantine attacks, right? I mean, it's good to be tolerant towards Byzantine attacks. Don't get me wrong, but you don't have to be,
Yeah. I mean, one main difference is probably also that for Byzantine attacks, in most protocols, you can attribute them to the attacker, right? And then you can slash them, you can punish them. That greatly reduces the incentive to actually try to do such an attack if you already know that the outcome is that you are banned from the network or slashed even and lose all your stake. Then why would you even try it?
I see. But that's the accountable safety part, I guess, if you
Yeah.
are malicious.
But I think it's a good point and a big picture sort of interpretation that it's usual in academia to think about faults, like all of them, right, in one category, be the crash or Byzantine.
Right.
But yeah, as you say, that crash faults are much more common. And then this is one of the things where we're like, okay, we should optimize for what's the problem in reality more often.
Yeah. So, I mean, this is sort of like, these are the 4 main ingredients maybe that Solana had before Alpenglow. And we kind of remove all of them, except Turbine, which we liked. We kind of replaced it with something a little bit simpler. But this is still related, I would say. And then we added, so we looked at the recent work, basically. We were inspired by some recent work on consensus. Here are 3 of the papers. And we added a voting component, which we call Rotor, to this Rotor. Okay, so these are the 2 new ingredients. In some sense, it's a big change if you want, right? So we kind of we removed 3 of the 4 parts, changed 1 part, and add another part.
So the 3 of the first, so if I'm, for our listeners who might be listening, the 4 parts are proof of history, gossip, turbine, tower. You remove proof of history, gossip, and tower. You retained a simplified version of turbine, which you guys are calling a rotor, and added a new part called voter. And the voter is the consensus part. Is that correct?
Yes, the Rotor is the data dissemination part, and the voter is the consensus or voting part. Yeah. So Rotor, the data dissemination part, just how this works. So it's a simple leader-based protocol. So we have blocks which contain transactions. So the blocks are just sequentially sent out by the leader. The leader changes over time, but that's basically how it looks like. And we do consensus of each block. But then each block is pipelined into what we call slices. So these are like, maybe just milliseconds of data or something for the data dissemination. And then the slices are split up in shreds, which are so-called coding shreds. And we have, so for each slice of data, for some amount of data, we actually had double the number of data in the shreds, with the idea that if you get half of the shreds, then you can reconstruct the slice. And if you can reconstruct all the slices, then you can reconstruct the block, and then you can do consensus on that.
The way to think of slicing, is it like, suppose assume that block has 10 transactions, and slice 1 can have the first 3 transactions, slice 2 can have the transaction 4, 5, 6, and the slice 3 can have the rest of the 7, 8, 9, 10. Is that the right way to think of the slices?
Except the single digit numbers break my heart a little bit.
Yeah. Is there a slicing algorithm or something like that special, or is it just some set parameters are there?
Well, the leader just collects transactions basically and then sends them out together. That's what the slice is.
I see. So the leader has all the power to decide how to slice those things.
Yeah, like it's up to the leader. It's up to the leader's scheduling algorithm to actually build the slices, and then in the protocol, it's just an upper bound on the number of bytes that you can have per slice. Because that's then how we distribute it, right? We have some fixed number of shreds. I think right now in mainnet it's 64 shreds, and this data somehow has to fit inside these shreds.
The idea is that each shred basically is a packet in the internet, so it obeys the MTU limit.
Yeah.
And this gives you then a limit on the slice.
Like each shred is supposed to be just one UDP packet, and so that there's no fragmentation on the network layer.
I wanted to mention that it's usual that the leader decides this kind of like slicing or ordering or whatever, but I thought it's worth mentioning that it's an active area of research for us, and we want to change the game in this respect.
So the leader sends basically these shreds. Now this is a single slice here on the screen. The leader sends the shreds to what we call relays, and they basically just send then their shreds to everybody. Okay, so that's what they do. let's say there's 1,000 validators in the system, something like that. They would just, every leader would just send their shred to 1,000 other nodes in the system. This can be done naively. This is very fast because it's all just UDP packets. But it could also be done with some, multicast service which exists in the Solana world, like something called 00.
So generally, in blockchains, or almost all blockchains, they have the leaders trying to disseminate the blocks by themselves. Instead, here it's disseminating to an intermediary set of nodes called relays. What exactly the problem it's trying to solve by doing this? Is it like some kind of bottleneck throughput?
I just want to say this is such a good question, and it's been neglected for a long time. I mean, the way you said it, you said that in some protocols the leader disseminates the block to everyone, and there are some protocols where this happens. I mean, what's more usual, right, is that you gossip the block. But either way, there's a problem. Like if the leader sends the block to everyone, I mean, even if there's just a few nodes, like even if there's, 20 nodes, not to speak of thousands of nodes, if the leader is supposed to send the data to every single one of them, like literally, right, then you immediately get 1/n of the bandwidth of this leader, like per node. That's terrible. It takes a lot of time. While in gossip, okay, you might think that it helps. Maybe, I mean, it kind of helps, but not too much in the sense that, okay, now you have many steps. The leader sends the block to some nodes, then some nodes send the block to some other nodes, and again, you have many steps. The problem with both of these scenarios is that most of the time, most of the nodes do nothing. So if you want to say it simply, what's really different in here is that most nodes, most of the time, contribute their bandwidth. It's a huge difference in practice in the sense, with respect to how fast you're able to disseminate the data.
Yeah, and it's very fault tolerant as well, right? Because you don't need all the shreds to put the slice together, right? Only half the shreds are necessary, let's say, if you have small provisioning vector. So it's fault tolerant and fast. And it's even more fast in some sense if you think about it. So the leader sits somewhere in the world, these relays sit somewhere in the world. And then if you only need half of them, then maybe the slowest paths you don't even need, right?
Yeah.
You just need the path,
Yeah.
the fastest path.
Yeah, because if you just look at the protocol, you think it's 2 network hops, right? But in practice, it's quite a bit faster than 2 network hops because you get the
fast thing that you guys are saying. This is something like forward error correction, where you try to find this is what content delivery networks do, right? With forward error correction.
Yeah.
So is that the similar principle here?
Yeah.
Same.
Okay. My second question is, suppose I am the third relay here. I'm running the relay. How do I know do I know which data shreds I should get from which slice? Like, is there some kind of a global understanding for each relay, which one they are getting, which shreds from which slice?
They wouldn't need to know it. The relays actually are very dumb in some sense. They really just forward whatever they get. But I guess, at least the leaders, of course, know who they are when they have to do something because they have to initiate something. The relays are chosen randomly. They don't even have to know that, right? The leader could even choose their best friends to do that for them or something if you wanted. So it's not necessary.
You guys are mentioning that it's much more fault tolerant. So how does the system ensures that this is not just the leader choosing their own friends, but it's robustified to a certain extent?
In some sense, I would say that the leader could choose is the most robust thing because the leader really wants the block to go to everybody. So to choose your friends hopefully helps here. But this is not the way we specify the protocol. This was just something we need to say that there's a lot of freedom here what to do. And this 00 multicast network, which is already something like 40% of the stake on Solana, is kind of connected to that. So there you can, for 40% of the stake, you can actually send them directly from the leader via multicast if you want it. You can do this on top of this thing here, just to have even more ways to get the data to the validators very fast.
I see. So this 00 connection that you're mentioning, multicast, it's a separate one from the relay system itself.
Yes, yes. And
Okay.
since it's all erasure-coded, you could use both at the same time, right? You could say as a user, no matter where I get my shreds from 00 or from this rotor, I can put them together into a slide.
That's fascinating.
Yeah.
I don't think any other blockchain is doing this kind of efficient like dissemination, right? Is the Solana is the only one with Alpenglow?
Possibly, but I think this is picking up speed right now. So I've heard others which are also thinking the same.
I want to brag about this. I mean, I shouldn't brag about this because I wasn't there to do it. But Solana really pioneered this technique, and in academia, it gains more and more recognition these days. This, erasure-coded dissemination in blockchain protocols.
Yeah, already Turbine did this. The only difference is that Turbine has multiple layers, which is something we felt is not necessary, but makes things more complicated and also a bit slower, right? Brings it closer to gossip somehow, which Kobi said before, makes things just slower, right? Because you have to send the packet multiple times until it reaches destination.
Are relays here incentivized, or is the assumption that they're altruistic?
Oh, they should be incentivized in a proper protocol. Whatever work you have to do for the protocol, you maybe should get something out of it. So there should be proper incentive.
That's the plan for the future, probably, I'm guessing.
We have something already in place, but it's not as good as you want it to be, maybe. It's not as complete as you want it to be.
I just want to say that this is a good question. I mean, you're saying, oh, there should be a reason why the relays forward the data.
Yeah.
I just want to say that it's not specific to Alpenglow or to Solana. This problem, I mean, it's okay, you could ask, why would, let's pick some other, I don't know, Ethereum. Why would Ethereum nodes gossip this and such data? In every blockchain protocol, some parts are not going to be incentivized, and it's a problem, and we should think about it, and it's a good question. I just wanted to say it's not specific to us in any way, really.
It's probably a general peer-to-peer question itself. Why do you propagate the data to someone else? Why do you behave as a relay to others?
Right.
Good. So this is the data dissemination part, the voting part. So here we again have the blocks, and you can see here in Solana, it's basically currently each leader does 4 blocks, and then it's the next leader's time. And then we use timeouts. So all the validators basically are referees just to check whether the block is in time. So this is the idea from Simplex. So you have some time. This is really local time, right? The nodes just have their system time or something. They know when the last block from the last leader, for instance, was received. And then they start a timer and they say at that point they want to receive the last block from the next leader, for instance. And then they can just vote yes or no, whether the block was in time or not in time. They don't do this just for the last block, they do it for all 4 blocks of the next leader. And this is important because if the first block is already late, then we might get rid of this leader very quickly if this leader does not work well. So then you basically vote yes or no on these blocks. Let's say we vote yes in my example here. So this is also something we just basically multicast out again, right? So it's just, we just send our vote to everybody. We don't have like 1 million, validators. We only have maybe 1,000 or something in Solana, so it's a bit lower. They sent this to everybody, their vote. So there's a few cases what could happen. So now I receive the vote. So everybody sends their vote to everybody. So everybody receives the vote from everybody. And if you get 80% or more of the stake voting yes, then this block is immediately final, okay? Then you can immediately build a certificate, which is a BLS type certificate. And you can immediately say, okay, here's a proof that this block was final. So within 1 round of voting, if you want. And then you also send the certificates to everybody so that everybody agrees or sees that as well. Then the other extreme is that you get a lot of no votes because the block was too late, for instance. Let's say you have 60% or more of the stake voting no. Then you can immediately build this skip certificate, which says we skip this slot, we skip this block, basically. Also that you can send to everybody. And then the only interesting case is between those 2 cases, essentially. and you have like a mixed thing between 60% no and 80% yes. There's many possibilities there. And in the mixed case, we have to do one more round of voting. So basically, it's not yet final. We cannot make a certificate right away. There's one more round of voting.
Want to restate what you are saying? There are two types of consensus protocol. One is where in every slot or in every view, the leader rotates, the leader changes. But in the Alpenglow, it's more like each leader has a fixed number of slots. It's not like every slot it is changing. In the example that you are showing, it's like 4 slots, the same leader is there, and then next 4 slots, some other leader is there. It's something like that. Is that correct to say that?
Yes, this is something we inherited from the previous protocol, so to speak, right? Like whatever we could keep, we of course wanted to keep. And it felt like a good trade-off to do it for a few slots. However, what is new here is if a leader is not compliant, then we can switch to the next leader much quicker, right? That's in some sense something new.
Let's take the 4 slots example, one leader, and in the first slot, if the block does not come, if the block is not proposed by the leader, then the whole system says we should just move away from this because this leader has skipped the first slot and we don't trust it anymore. Let's just move to the next leader as soon as possible.
Yes.
That's the philosophy here, right?
Yes, very much so. Skip means skip for the rest of this leader, essentially. We go directly to the next leader.
There are like bunch of protocols where, like previous consensus protocol, where 2 or 3 rounds take place, where only one block is being voted upon, but after that finishes, then the next block voting starts. In Alpenglow, is it like it does not wait for the whole consensus for each given block to finish, but immediately after the first slot, a block is proposed. In the second slot, another block gets proposed. It's like very pipelined. Is there an optimistic block construction is happening or something like that is happening here?
If you have been the leader before in some sense, then you can just continue piping out stuff. You would trust yourself that your block gets in, right? So you can be optimistic. So the only interesting case in some sense is you have a change between leaders, right? And yes, then you would do something where you start already producing things as the next leader. Hope that the previous block gets accepted. At some point, you have to say who your parent is, right? Again, if you're your own parent, if you were the leader before, then you can trust yourself that this works for you. But if you're the next guy, then you would say, then you wait, basically. You put that in the block. But blocks take 400 milliseconds, so there's a bit of time to put this parent relation in there.
You were asking if we vote on blocks sort of concurrently, right? And I just wanted to say, yeah, we do. Like you don't wait for a block to be finalized only to be allowed to vote for its child or some other block. So we do have, you vote for a block, then you might not see any decision with respect to that block yet, and you might already vote for the next block on the next block.
My understanding of the optimistic was in the corner case, which Roger actually touched, is when the leader gets changed. Suppose leader 1, 4 slots done, and then the leader 2 comes for the next 4 slots. So it has to make some guess that, it has to tell what is the parent, right? Something like that. And
yeah, there we have a small optimization which does that, where you actually start building a block on one parent. If you see a block in slot 4, you start building a child on that block, and then if you later see that consensus actually decided on another block, then you would basically switch the parent and basically restart your block, kind of.
Okay. So, and the switching protocol is a different part. Like, how do you switch?
I mean, I would say it's like a small extension. You could do Alpenglow without the small extension, and we just put the small extension in there.
I wanted to say it's a very good question, right? And it relates to whether it could or could not be possible, for example, for a leader to kind of trick the next leader, right? Like maybe something funny happens and then the next leader builds a block, but then it turns out the ancestor of his blocks was actually decided against. It was rejected. So it is a problem in some protocols, right? If they don't address it, right? You could have this thing where one leader might potentially trick the next one. But yeah, I mean, we do take care of that. And there's this, I mean, what Quentin mentioned, right? This optimistic Okay, it's optimistic for a moment, but then okay, the next leader, after it does the thing where it might or might not switch the parent, right? It has a guarantee that its blocks are going to be accepted. I mean, if it's correct and everything.
That's true. This was the whole the block proposal part. So I want to go a little bit deeper on this finalization aspect for each block. The first one that you were mentioning, that it takes 80%. If 80% people's voters say, yeah, we agree on this, immediately it gets finalized. So this is some kind of fast finalization.
Right.
And suppose 80% don't agree. So is this like parallel, some kind of parallel fast path, slow path protocol? Is that something like that?
Yes, very much so. So what actually happens is, so you're sitting there as a validator and you collect the votes of the others. As soon as you see 60% yes votes, then you already send out the second round message, basically, which will be the finalization for that, the finalization message. But then you keep collecting votes for the first round, so to speak. So now what could either be that you reach 80% for the first round, or you reach 60% for the second round as well, because others also have to send this out. And whatever is faster for you is where you get the finalization. And it could be that for you, maybe 80% is faster, but for me, 2 times 60% is faster. This is quite cute, actually.
And we actually do see that in practice. Like,
Yeah.
there are nodes on the Solana mainnet where one is faster, and there are nodes where the other is usually faster.
But the protocol is safe enough that suppose one guy gets the 80% faster and the other guy gets the 260% faster, they will still finalize on the same block, right?
Yeah. These always have to have the same.
If they didn't agree, the protocol would not be so cute.
Yeah.
Right. But I really want to hammer this in because I think it's pretty counterintuitive, right? That in the same execution and for the same slot, for one node, one is going to be faster, and for some other node, the other is going to be faster, which is, yeah, I think in theory, it's often like, I think it's very important in practice, and typers, they often forget about it or they don't even like look at it.
Yeah.
I mean, in theory, it would be difficult to even analyze this because there you usually have these rounds, right? And you say, how many rounds does it take? And then people would say, well, obviously the 1-round protocol is faster, but here the 2-round protocol can be faster in practice, and actually maybe, yeah, often is.
Yeah.
One thing you mentioned, there's a concept of timeout for like leader rotation, like all this thing. And you're mentioning that it's this timeout is based on each node using its own local clock for timing out. There's no need for a global clock. And Solana had this global clock called proof of history. That proof of history is no longer needed, right, for this. It's just locally I'll just time it out, and other nodes will just use their local clock to time out. Is that the notion?
Yeah, it's only local clocks in this part, right? Local clocks do drift a little bit and whatnot, but it does not really matter, right? In the grand scheme of things, because what matters is that we have 60% good nodes. Otherwise, if you have less than that, it would be a problem. This was an early latency histogram, which kind of summarizes the whole thing. This was for a leader in New York. And basically the green curve would show for 100% of the stake, so it goes up to 100, how far they are from New York. This is just network latency, let's say. Maybe this is 200 milliseconds. So some people are very far from New York, some of the validators. You can see here some geography, right? Some European nodes, some American nodes, how far they are from New York. And on top of this, we show how much slower Rotor is, how much overhead it adds. And it's not much. You see, for some nodes, it's really just basically the network latency plus a little bit. For some, it's more, but that's roughly it. And then you can see how long it takes until you have 60% of the votes in the good case. This only shows the good case. And then it shows how long does it take until finality, whereas finality here could be 80%, or it could be 2 times 60%, Or it could also be that you just receive a certificate from another node that it has finalized, right? It's also possible that this could be the fastest thing. So whatever is the fastest thing gives you finality, and this kind of shows that the overhead of the protocol is roughly maybe 2 times the network latency or so.
So this was the whole architecture. Now let's talk about the incentives, because I'm sure that the economics are changing with with like what validators have to do here, what relays have to do. One of my question is, so previously votes used to be put into the on-chain, right? People were voting on-chain the votes. Now the votes are not on-chain. It's like it being gossip, like all-to-all propagation is happening across the peer-to-peer. It's off-chain happening. So how, and that means your the fees from the voter transaction is not there anymore. Your ledger is not growing that fast. This definitely changes how much work validators have to do for storing data, for what kind of verification they have to do, because the voter transaction is not there. Can you talk about how does it changes the validator economics in general? That does it make the validator, running a validator software is cheaper?
No, these are good questions, and somehow these were the most, when we presented the Alpenglow, of course, the validators only cared about the parts you just asked. How does it change our economics? So before they had to send votes to the chain, and that actually cost them something to send votes to the chain. This was like a transaction that they had to pay per vote, and they would get rewards back again in some sense. But if you were a very little validator, then maybe it would not even be worth to send the votes to the chain, because it would cost you more to do that than to get the rewards. So now the votes are just sent directly. There's no more, there's no more cost of the blockchain in some sense for votes, and this relieves them of this cost, which is part for their cost. However, we didn't want to change the economic game too quickly immediately. We wanted to kind of keep it a little bit similar. So what we now have is we introduced this VAT, it's called, or some sort of a tax essentially, which you have to pay as a validator to be part of this, right? So every epoch, every 2 days or so, you have to pay a small amount of money to be part of this. This is less what the vote used to cost, but it's in the same ballpark, so that we kind of could argue that the economic game didn't change very much.
So this is for smoothing out this transition, this tax, and eventually, I'm guessing this tax will be removed.
Could be removed, or more, like that we have real economics in some sense. So let's put it this way. So this is a bit my view, but the question is a bit how many validators you want to have to make the system secure, right? So if you have, let's say, 1 million validators, then of course there's more protocol overhead, right? Everybody has to get the data, everybody has to get whatever, right? You have to build around this. And let's say if we would remove this tax completely, then maybe we would have 1 million validators, right? And that would be problematic for us in some sense, right? Not that it wouldn't work anymore fundamentally, but it would be slower or something. We maybe don't want that. So it could be that we just find the right economic incentives eventually. But, like as with every blockchain with governance, right, you have to ask the people who are the validators whether they agree with this update. And we felt if we make it somewhat a zero-sum game for them, or maybe a bit of an incentive, but not much, they would still agree to the protocol change. And then we can then tackle this later. Okay, this the real economics.
Suppose the next epoch is coming. So in the previous epoch, you have to pay the tax for participation in the next epoch. Like how to think about this?
It's exactly what you say. You have to put up the money first, so to speak, to be part of this. Yeah.
It basically becomes part of the epoch change mechanism, right? When we determine the set of validators for the new epoch, then we take this into consideration, right? We deduct the fee that is required, and if you cannot pay the fee, then you're not in the next validator set. And otherwise, we take all the validators who paid the fee, and make that the new validator set, right?
The other question is, how does the MEV dynamics gets changed? Given that now the finality is in the order of hundreds of milliseconds, so you have to be even faster. I mean, that's probably like to even extract MEV. Does that to centralization in that case, because only bigger ones can do it and they only can participate for doing this? But on the other side, there was a goal for reducing the cost for running validators so that it gets more decentralized. So it seems like there is a push and pull happening.
No, I mean, decentralization is super important, right? And it can mean various things. And so I would say it's not clear to me why something is more decentralized if you have very big validators and tiny validators together. Okay, so but let's say geographic decentralization, of course, does matter, right? You don't want all of them in the same location for security reasons and other things as well. So we try to build the protocol around the idea that you would not have an advantage. We try to have to build the protocol such that there's no advantage by sitting at the right place, but you can only do so much. Let's put it this way.
I just want to say sometimes hear, or we sometimes hear this, it's like a concern or this association that something about MEV gets worse, but the way I understand it, it only gets better. And for a few reasons. So one reason, okay, you mentioned latency. Actually, Alpenglow, it equalizes the latency between like validators that are in some cluster, let's say in Europe, that's where most of the stake is these days. So Alpenglow evens out the latency differences, like going from today to Alpenglow for the remote validators. So their latency should improve more, then it improves for the ones that are already somewhere in the center of the universe. Okay, in this sense, yeah, I think it's only better for remote validators. That's one thing. Another thing, so Tower, there were some nuanced like misbehaviors that you could employ to take advantage of like some other validator, right? And the better connected you are, like if you're in the center of the universe, maybe you could play these tricks better. Now, Alpenglow addresses some of these problems. So again, I mean, the only ways in which I see the landscape changing for MEV, I think it's for the better.
Here, better means more efficient extraction of the surplus that might be there.
No, more efficient like I'm not sure if that's what I meant. So you mentioned centralization. Okay, so centralization is something. Well, it's a force where if you have an optimistically responsive protocol and there is a cluster that is well connected, and the latency for these guys is going to be better than some nodes in remote wherever in Antarctica. Okay. Then you're gonna argue the node in Antarctica has a disadvantage, right? So maybe he gets less money for this or that reason. Now I'm saying, okay, it's always going to be the case that if you have a node in Antarctica, it's a bit worse for you, or like maybe you get less money. Now I'm saying for Alpenglow, this difference is going to be smaller. It's going to be better for the guy in Antarctica. This force of centralization, I mean, in the sense of incentives or MEV, like it's pretty much in every protocol. You would have to get really esoteric to equalize it perfectly. But Alpenglow makes this difference smaller. It does not exacerbate it; it improves it.
Now that we have talked about the economic side, we want to talk about the integration with the other components of the Solana ecosystem. So you have other things like 00, multi-proposer architecture, all this going on. So my first question is, how does this interact with the like multiple concurrent proposals? Does the integration is very straightforward, or is it there are nuances to this integration?
It depends a bit who you ask and what kind of solution we ultimately have, right? So we have a few proposals in the pipeline. Also, people start already programming things, testing things. I would say for all of them, Alpenglow is somewhat a necessity. Okay, you would not want to do it with the previous protocol because it's just too complicated in some sense. The simplicity of Alpenglow helps to make this happen. and some integrate very nicely with Alpenglow. You have to do very little things, and you can already could have these multiple concurrent proposers. So this is true. This is, I would say, the other big project at Solana for this calendar year. So Alpenglow will be released, I would say, for sure in the first part of the calendar year, and then shortly after, probably we'll see a multiple concurrent proposers solution as well.
And this MCL solution is just plugging on the top. Like whenever the proposer is leader is proposing the block, just before that you get it from the multiple proposer. Is that simple, or is it?
Some of the proposals are that simple, but there's 3 or 4 things, right? And we're still discussing which ones we're gonna do, and no matter how we're gonna do it, it's we'll first come up with a very simple one, but I would say the simplest ones we have are of that kind that we maybe just have multiple proposers, multiple leaders at the same time, and then vote on, what have you seen or something. It's quite compatible, I would say, with Alpenglow.
Next question: What needs to be changed at the RPC or the WebSocket level? Do they have to upgrade their infrastructure for Alpenglow, or is it same as before?
Yeah, that's also a good question. Why do I have to take the hard question? So in some sense, they don't have to change anything. So if an RPC is willing to pay this VAT, the fee, then they can just be part of the protocol. That there's nothing they have to do. They are first citizens in some sense, get it as fast as anybody else. If they don't want to pay that, then it will change for them, I would say. Then they have to get the data from somebody else, which is also possible, right? They could get the data essentially secondhand from any set of validators. They get it firsthand or something like this. You can offer it as a service. Also there, we will have several paths, I would say, for success, depending on how good your service should be and how much you're willing to have this cost you. But there will be very low cost versions of this as well, maybe zero. Many RPCs are maybe also somewhat affiliated with some validators, and there it will be very simple that they just say, whatever I get, I forward to you.
I saw somewhere that few of the Solana programs, they need some notion of global clock, and PoH is being removed. So what is the plan for those kind of Solana programs? Like, do those app builders have to rewrite their app, or is there something that Alpenglow will come inbuilt that will help them in navigating this?
Yeah. So we will have something like a clock still, so something like a real-time clock, right? This is something which now is for free, basically, because when you vote, you would also tell what the time is, and then everybody sees what the time is, so to speak, on chain. This we will not have anymore because the votes don't go on chain anymore. But we have a simple, I would say, approximation of this somehow. The idea is very simple. The leader would just add their time to the current block. Just add the current, however they see the universal time currently. And basically, they are not allowed to deviate too much from the parent block time. Okay. So they should be honest, but let's say if the time is a bit behind, they cannot catch up too much or they cannot slow down too much. Such that if most leaders are honest, then the time should always be around the right time. But if you're unlucky and you have, let's say, 10 leaders in a row which all want to slow the time down, 10 malicious leaders, so to speak, then this could also happen. Then it slows down a few seconds, and then the good leaders coming in will speed it up a little bit again. But so it will not be a super exact time, but we believe for the applications that are out there, which usually need the kind of correctness of about, an hour or something like this, it should be good.
What is the planning for this migration? Ethereum did a similar kind of transition back in 2022, which had like a lot of detailed planning on. Is this something on those lines? You guys will have also detailed planning on how to do this migration?
It's a hard problem, I would say, generally to make this happen, right? So this is, as you say, it's a huge update for Solana. It needs planning, but it's not that we have an exact timeline now. I went on stage at some point and said maybe at this time we would already have it, but that was maybe a bit too optimistic. I would say most of it is implemented in the client of Anza. So in the Agave client, the implementation is roughly complete. I would say it's running already in some smaller test nets, but some of the corner cases are maybe not yet fully implemented. If things go really bad, right, we also have to make sure that we have those. But we have a plan how to do the migration, how to switch from the old protocol to the new protocol. And this has to be like this, right? So the protocols are very incompatible, so everybody has to switch at the same time, essentially. This I would say is a difficult thing, right? So in distributed systems, this is one of the most difficult things if you have 1,000 nodes which all have the same switch at the same time safely, right? So that's sort of I would say, that's something we have to worry about, but we are not alone, right? There's
Any tentative date on when this switch might happen, like this quarter, Q2, Q3?
No, it should. Q3 might be late, I would say, but it depends very much on the testing phase, right? So we will have to extend the testing on this on some testnet before we actually go to mainnet. And now this could be faster or slower, in my opinion. So I don't think once the testing is done, then it can go fast, right? But until then, I'm a bit hesitating to give you a date because it could be that we run into some issues that we have to solve then.
We covered a lot today. So we've unpacked Alpenglow as a system and what this means in practice. Roger, Kobi, Quentin, thank you for walking us through both the motivation and the mechanics behind Alpenglow and its impact on the rest of the components of Solana. And to our listeners, if you're building and operating in Solana, this is one of these moments where the stack is changing quietly but fundamentally. So thanks for listening, and we'll see you in the next episode.
Thanks so much for having us.
Yeah, thank you.